Hello, everybody. This is Johna Johnson and John Burke from Nemertes, and we are here to talk to you about what is quantum computing good for? And that's more specifically, I know, right? There's no real point to this quantum computing, but it sounds really cool. Um, so this is us. I'm the CEO and founder. John is the Chief Technology Officer. We've kind of swapped roles a little bit. I had been, before starting Nemertes, I was a CTO, so we love to argue about technology and search into its benefits for you and for our clients. So here we go. Um, I always like to kick off any interesting area talking about the people who've actually created it, because this didn't come out of, out of the sky on the like the Ten Commandments. This is quantum computing is something that was actually kicked off by a particular individual who is David Deutsch, who is currently a professor at the University of Oxford. I'm not sure where he was in 1985 when he wrote the seminal paper that said you could use quantum mechanics to do quantum physics to do computing, was essentially his massive insight. He's now gone way beyond that and has been talking about all sorts of really interesting algorithms in quantum computing. In any event, he has a great quote that allows me to really conceptualize the kinds of problems that quantum computing solves well. And that's the idea that it's the first technology that allows useful tasks to be performed in collaboration between parallel universes. So you can basically solve lots of what if problems by assuming all the different what ifs at the same time. What if I were 5 feet, 5 feet 6 inches instead of 5 feet 5 inches? What if I were blonde? All the different immense universe of what ifs you can be looking at the same time. So how does it work? John, why don't you kick off that discussion?
Sure. And the key difference between classical computing, which we're used to working with all day, every day in our day jobs, and quantum computing is that instead of working with at its base a strictly binary quantity, something that's either a zero or a one, a transistor that's either on or off. Quantum computing relies on what are called qubits, which have ostensibly two states, just like a traditional classical bit, but it's a quantum physical characteristic that's in one of those two states. So we talk about quarks having spin or polarity. They can be spin up or spin down. They can be horizontally or vertically polarized. Those are the two states that qubits can achieve theoretically, but as we know in quantum computing and quantum mechanics generally, nothing's ever 100%. So no state is truly binary, and it's as though you've taken that classical 0 and 1, which is integers, and turned it into two ends of a real number line, and all of the possible states between 0 and 1 are also achievable. And so quantum gives you that whole sort of infinite fuzz between those two integers to work with.
So, John, basically my next rock band is going to be called Infinite Fuzz. I'm sorry, that's very good.
Well, and they can sing quantum computing, what is it good for?
Yeah, right,
Which is what I was thinking
exactly.
earlier.
And it's exactly that ability to be anywhere on a spectrum. Like when John and I were talking about this previously, we figured out that the best way to articulate this is if we've all been trained in computer science in binary. It's either 0 or 1. And of course, we all know that our standard human numeric structure is I keep wanting to say hex. It's actually decimal, so it's anywhere from 0 to 9. What John came up with was this idea of, well, let's just say it was anywhere on the real number spectrum, so it doesn't have to be an integer. That kind of gets across this notion of what quantum computing does and is. And what that means is that because it's a spectrum, because it's fuzzy, it's infinite fuzz. I love that. That it's really good for looking at lots of things at once is kind of the way to put it. And the other thing to keep in mind is that there's this concept of noise that doesn't really exist in transistors. I mean, yes, transistors can be noisy, but basically good engineering got that down to the very simple question of we decide at this point that this is either a 0 or 1. Well, if it's maybe going from 1.17354 to 1.18, where are you drawing that line? And that's where the noisiness kind of kicks in. Also, because it's quantum, simply reading it can change the state. There's also one last concept that really is important to understand, which is this concept of quantum entanglement or action at a distance, which means you can have two particles or two things very far away that can actually communicate with each other, even if they're not physically co-located. It seems like it breaks the speed of light, but it doesn't for complicated reasons beyond the scope of this presentation, but leading to some really interesting ideas. So with that, let's talk about what some of the implications are specifically for quantum computing. Um, so, one thing is that for certain types of problems, and this is something that Deutsch proved back in the 80s, that it can be much, much, much faster than traditional computing, and therefore sort of breaks through Moore's law in terms of the physics of improving year over year. That's actually kind of a big deal because it means that what we thought was a physical limitation isn't. The second thing is, as I mentioned, the whole notion of entanglement means there's correlation without connection, so it's really the ultimate in a wireless network. I seriously doubt we're gonna see, quantum Wi-Fi anytime soon, but it is kind of a cool way to think about it. It's also the case that because it speeds up many kinds of problems, it can break many conventional cryptographic systems, but it can also, and we'll talk about this, create more secure systems overall, not necessarily from the point of view of cryptography, but from the point of view of overall systemic resistance to being hacked. As you know, a more specific example is that search algorithms, for example, can be speeded up by several orders of magnitude, which is huge. And John's favorite example, simulation of complex physical and virtual systems can be really improved so you can get things like accurate weather prediction. I mean, we're pretty close, but we can get a whole lot better with quantum. And that's not just weather predictions, but it's also anything having to do with science. So geology, chemistry, anything with scientific reactions can be super well simulated now. Finally, that last bullet item, we're already seeing that quantum computing and AI is giving us big changes because, in a way, they're almost orthogonal. And what AI brings to the table is the ability to analyze certain things and come to a reasonable conclusion very quickly. And what quantum computing brings is the ability to compute other things and come to a resolution quickly. So those two things together end up working really well. Also, it's worth noting who is playing with quantum. Well, it's the finance fintech firms. Certainly, anybody who's interested in digital ledgers, which is the new cool way to say cryptocurrencies, because to be honest, cryptocurrencies were always a little bit sketchy, but digital ledgers are for real, and real
Ponzi
banks are
scheme.
using. What's that?
I said Ponzi scheme.
Yeah, exactly. Ponzi scheme, cough, cough, Ponzi scheme. I mentioned earlier, anyone who's doing physical systems, weather prediction, chemical companies, they're already using it. Quantum finance models are useful, likely beyond finance, just like Monte Carlo simulations, which I did way back as a young particle physicist, are actually way useful in lots of scenarios beyond physics. So this is good because essentially the richest companies are spending boku bucks to figure out both the use case and the solutions, and the rest of us can kind of ride their coattails. Oh,
I just wanted to point out too that there's been some interesting work in, of all places, uh, automobile manufacture.
yes.
And one of the earliest practical applications for industry was about painting cars. So things are already getting traction in the market uh, based on quantum computations.
And now that you've mentioned a really practical physical example, one of the questions I was asked for a presentation I'll be doing in June is, yeah, but are there really any actual quantum computers as opposed to the simulations that are living up in the cloud? And the short answer is yes. It's beyond the scope of this particular presentation, but yes, there are real world quantum computers with qubits that are now in the dozens, but moving up quickly to the thousands. And that's a very big deal because the idea that quantum computing is something that is going to happen in the future, is very 2015. It's happened. And in fact, I was actually talking to the Wall Street Technology Association yesterday, and one of the people on the call piped up and said, yeah, could we please make sure that we don't consider quantum computing as part of emerging technologies because from our point of view, it's emerged. So that point is very important to make. So what are people doing with this? Well, quantum variational algorithms are really cool because it's essentially a hybrid. If you think about any new technology, it usually gets adopted in a hybrid form. So you say, okay, some of it is going to be classical, which is the word for legacy or historical computers, and some of it's going to be quantum. That's where you get something like AI plus quantum because the AI is actually running on classical computing. Goldman Sachs has a partnership with Honeywell, which bought Cambridge Quantum to exploit variational algorithms to predict stock and option prices. They being Cambridge Quantum, also developed an algorithm that speeds up my favorite Monte Carlo simulations by 2 order of magnitudes over classical machines, which is a very big deal because Monte Carlo simulations are kind of the classical way to try to sort of spray all the possible infinite scenarios and see what pops up. I used Monte Carlo simulations to figure out where to put detectors in particle physics experiments. They are also used in financial risk analysis, supply chain logistics, drug development, et cetera, et cetera. And John, I believe the next one is over to you because we want to talk about the kinds of problems that quantum computers do well.
Oh,
Oh,
sorry.
and I
We
clicked
both
too
hit forward
fast.
there.
There
Okay,
we
you
go.
stop and I'll go.
There we go. I keep my hands away from that screen.
So re-emphasizing something that Johna just said, real quantum computing hardware does exist now. And although its capabilities are pretty limited, it's serving as the engineering demonstration of how to build even bigger quantum computers, bigger in the sense of having more qubits. And there are multiple vendors working at the hardware level. IBM is probably the biggest and most aggressive of the traditional computer manufacturers. Honeywell is in there as well, and there's plenty of startups in the field. IQM, which is like the quantum IBM or wants to be going forward. Folks like them are out there. And some of them are working exclusively on the general purpose quantum computing model, which is sort of what we've been focusing on. There are also quantum computers that are focused on specific categories of problems that work in a very specific way called quantum annealing around, sort of settling into the optimal energy state for a given problem. They're only useful for certain classes of problems, which actually we'll touch on in a minute. But for those problems, they can now solve in reasonable time previously unsolvable problems. And in fact, that example I mentioned earlier of car painting, that was solved on a quantum annealing machine. As I said, right now, though, the qubit counts are kind of low in the dozens to hundreds level of qubits per machine. And more importantly, in some ways, those qubits are kind of noisy, meaning the preservation of quantum states is not perfect, is far enough from perfect that dealing with the level of noise in the machine is just as important as getting more qubits into the machine. However, things are improving very quickly. And, whereas in 2019, we would have been speaking almost entirely in hypotheticals terms. We're at the point now where IBM is standing behind its prediction that it would have a 4,000 qubit computer in just a couple more years. And that's another order to 2 orders of magnitude above what folks are working with now. So that's pretty impressive level of progress. And 4,000 qubits is enough to do a lot of very serious work. So in preparation for that and working with these smaller qubit count machines as test beds, folks are developing programming languages. They're developing simulators for full quantum computers that they can test their algorithms on, and hoping to basically hit the ground running when those more advanced machines are available. So as I said, the kind of problem that you're looking at is really crucial because quantum computers can provide enormous speedups on some kinds of problems, whereas on other kinds, they won't perform even as well as a classical computer just because of the nature of the problem versus the nature of the machine. And so it's time to revisit undergraduate computer science and our wonderful P versus not P problem. So in looking at an algorithm that can solve a problem, we talk about first the class of P algorithms, or the class of algorithms called P, which can be solved, and the solution can be verified in polynomial time. So in practice, and this is the world of classical computers, the faster a computer can process things, the faster it can solve the problem or verify that the solution is correct. A larger class of problems is the NP problems, and those are the problems for which a solution can be verified in polynomial time. So if somebody says, here's the answer, you can check it in polynomial time, but you can't necessarily solve that problem, find the solution in polynomial time. Breaking a large integer down into its prime factors, that's one example of an NP problem. And actually, because it's not simple to solve, it is one of the bases of modern cryptography. NP complete problems are a different class of NP problems that you don't know whether they're solvable in polynomial time, but you do know that any one of them is morphologically the same as any other of them. So you can convert any NP complete problem into one of the other NP complete problems. And if you can solve one of them, you've basically solved all of them. So that's a special subset of NP. And then there's NP hard, which we all know and love as traveling salesman class problems, because these may or may not be solvable in polynomial time, and you might not even be able to verify the solution in polynomial time. And the traveling salesman, the problem of how to optimally hit all of the nodes in a graph, or all of the cities on the traveling salesman's potential territory, that's a classic example of an NP hard problem, where basically you just wind up trying every combination to see if it's the best one and then move on.
Which is generally how I solve problems anyway, which is not very efficient. But I do want to toss out a kind of some foreshadowing here, which is sometimes it's not actually necessary to know that you have an optimal solution, but just a solution will do. So hold that thought as John continues.
Hold that thought all the way to this slide. Because as John has said, sometimes it's enough to know that you're close, or that you're probably right. And that brings us to these sets of problems that are called bounded error problems, some of which are the BPP problems. There's a bounded error state, and you're going to probably get the right answer in polynomial time. And that's for classical computers. And then BQP problems, where there's a bounded error state, and you're going to solve it using quantum methods, and again, in polynomial time. A bounded error state means you can't prove that you've got the right answer, but you can prove that you're 95% likely to have the right answer, or 98% likely to have the right answer. And the point is that if you can define a level of probability that you've got the right answer that you're comfortable with, if you've got a BQP problem, you can then work that on a quantum machine to get within that error boundary. And then you've got an answer that you can work with, right? Because you're comfortable that it's 97.8% likely to be the right answer. And so that takes a lot of problems. The BQP class takes a lot of problems that are not actually solvable in a reasonable amount of time on a quantum computer, and moves them into the solvable in a reasonable amount of time on the quantum computer category, which is a useful category to have them in, because now you can actually start doing things. Johna, over
Yep.
to you.
And so I will toss out also the wild card when we're looking at problems. One of the assumptions, the implicit assumptions in everything John has said, is that the problem must be treated in isolation as a pure computing problem. What happens if that's not the case? And that's exactly what happened. Some Swedish researchers earlier this year broke the NIST recommended quantum hardened encryption algorithm by deploying recursive training AI with side channel attacks and a quantum machine. They basically combined the two, and they looked at stuff like, as the processing was happening, what was going on in the power consumption of a USB stick. And when they were able to do that, they were able to arrive at what the solution was by going outside the bounds of the problem, because they're looking at things like the physical environment, the physical computing environment. That's a whole class of problems that, if you have quantum computing plus AI together, you can get answers. And actually, NIST is looking pretty silly at the moment, because way back in the dawn of time, in July 2022, they were like, hey, we've got some decent algorithms that'll last for the next couple of years or several years. And in April 2023, which is back when this happened, they had nothing to say. So it is a wild card, but it's one to keep an eye on.
And it's important to keep in mind, too, that if you don't have access to the physical environment around the encryption activity, you can't use that side channel attack. So if you've just captured some data that's been encrypted using this algorithm,
yeah,
you don't really have any good hope of decrypting it. It's only if the environment itself is compromised that then you can also compromise the algorithm. So just, to give folks some hope, if they'd already dived on and
yeah.
committed to that algorithm.
Yeah, actually, my message to folks is, it's not time to worry yet, but it's getting a little uncomfortably close, is kind of the way I would put it.
Fair enough. Fair enough. So we can see then that quantum computing is good for several classes of problems. The BQP problems that need to be not so much verifiably solved as verifiably close enough to solved. If you can find a solution that's acceptably close, and it's like doing a numerical approximation of a non-repeating, non-terminating decimal number. I can calculate as many digits of pi as you need me to. Tell me how many you need, and I'll give them to you. BQP can do that. It's like, I can get as close as you need me to in a reasonable amount of time, as long as it's not complete.
John, you really do think like a geek, because my example of this particular problem is, it's like if you set yourself the challenge of marrying the most beautiful woman in the world, you can never do that, because it's not possible to solve for the most beautiful woman in the world. However, if you say, look, I need a woman who is at the 99.99% of beauty by whatever my measure of beauty is, that you can find, and you'll probably find, depending on how high your level is, several 100,000 that fit that. And any one of them will do. So that's the example I like to use. You're out there computing digits to pi.
Well, I think about pi a lot.
And,
I can't bake a perfect
strawberry
pie, but if you give me a target.
strawberry rhubarb, I think, is your preference, but I'm
Oh, that's my favorite to eat, but lemon meringue's my favorite to make. There's also the NP problems, and especially when you can solve that with hints from classical computing. Quantum computers can dive in there and solve things. And the NP hard problems, where in the classical world, your only real approach is to try all the different answers until you get to the one that you think is right, are perfectly suited to quantum computing, because, as Mr. Deutsch said, you're getting collaboration among all these universes where each one of those solutions has been tried, basically on the hardware at the same time, settling into the ideal state, because quantum.
right. It's basically like having Facebook way back, the way it was originally designed, and you can look at those several 100,000 of the most beautiful women in the world and pick one, kind of thing, as a visual way to look at it. So essentially, the moral of the story is, everything everywhere all at once is a great thumbnail way to remember what problems quantum is good for. So what does that actually look like in the real world? Well, we did a little bit of brainstorming and talking about it. Obviously, as we said at the beginning, what it's already being used for: classical financial and physical system modeling, weather prediction, John's favorite. Also, you can start
Protein
thinking
folding.
protein folding, chemistry, yeah, all that fun stuff, geology. Also, you can think about things in enterprise environments, like reducing network complexity by solving for all possible routes simultaneously. A side note, those of you who are not in networking would not believe how incredibly primitive most of our routing algorithms are, simply because routers have limited ability to do real-time computing, and so essentially they're just working from prefab route tables, which they update and refresh by a variety of mechanisms. If there were some way for them to be for every router to have access to every possible route in everywhere in the network, things would actually operate very differently. So that's one possible area for looking at. My favorite, and this was a conversation that we had yesterday with the folks at the Wall Street Technology Association, is this ability to do policy hardening. If you remember, we said, oh, quantum computing can actually improve certain aspects of security. The idea is, again, everything everywhere all at once. Let's take a policy, make one tiny change, and see if it's better than without the change. Now multiply that by all the possible tiny changes you could be making to that policy, run the simulations, and you should be able to break down the policies into at least, good enough, not good enough, and awful, and pick one policy from the good enough bucket. And that policy can be anything from a technology policy, a secure cybersecurity policy, all the way to something like a digital ethics policy governing your use of AI. So policy hardening using quantum computing is actually a really, really promising area. So you can break blockchain and encryption codes, but you can also provide 360-degree threat simulation, again, using that everything everywhere all at once version. So yes, it reduces security because it breaks cryptography, but increases it by providing this simulation. And now when you start thinking about simulations, now you've got military and geopolitical planning allows you to do things like, what if this country invades that country? What if this country invades that country, but doesn't do this other thing? And it's a sort of special case of policy hardening. And you can start playing out everything that could possibly happen in the war or in anything leading up to the war, thereby preventing the war. So hopefully you're getting a little bit of an intuitive sense of the feel of problems that can be solved. And John, I don't know if you have any other thoughts, anything that's worked for you when you're looking at a problem.
Well, I was actually thinking about infinite fuzz just now. Uh, on the security front and simulating attacks, one of the classic ways of testing your software is input fuzzing, where you are sending stuff that your system absolutely expects to get, but then you're also just basically doing random fuzzing of those inputs to see if there's any inputs you can shove into it that will break it. Overflow buffers, or provide access to something you weren't expecting to get, or otherwise breaking the software. And theoretically, with quantum in the mix, you could test all of the fuzzing at once for 16 bits, 32 bits, 64 bits of an input field.
Yeah, and by the way, now we've got the name of the band, Infinite Fuzz, and a few of the tracks, Noise in the Machine and Quantum Annealing. I just need the music. But so this is all great. You're listening. You're like, okay, so basically, Nemertes, you've told us quantum is real. Quantum is here. It can solve a bunch of real world problems that I might or might not have, depending on who I am, or might expect to have in the next couple years. What should I do about it? Step one, have somebody in your organization responsible for quantum. So create a quantum center of excellence. There are tons of resources for skills development and exploration, as John mentioned. Actually, I think you mentioned it before we started the webinar, but one of the challenges is, how do you break down a problem like policy hardening? How do you define that problem well enough so that the quantum computing can solve it? Well, the answer is there's lots of quantum programming languages being developed. So now is an excellent time to get your people in the Center of Excellence trained up on these quantum programming. We don't know which language is going to win. So, do bake-offs, have lots of different ones, and do proofs of concept to see, things like you can use quantum. I mean, quantum augmented risk assessment is something we didn't really talk about, but again, it's a special case of policy hardening in a way. It's like, well, what do I do about the risk? So there's lots of things you can be doing while waiting for the next couple years for these quantum machines to come out and be affordable. And you probably should be doing them even if you think quantum doesn't apply to you. So that's kind of the message here. I'm going to go ahead and wrap up now. Thank you very, very much for your time and attention. And John, do we see any questions? I keep meaning that I'm supposed to ask about questions. I am not seeing questions up here. If you do have questions, please go ahead and ask them. Meanwhile, I will just draw your attention to a couple of things. First of all, it is the upcoming talks that we've got. Next up is John talking about automation. Can't live without it, so you must learn to live with it. That's happening Thursday, May 4th. Uh,
And I
yeah,
just got to call out, they dredged up the oldest photo of me I can imagine there. I
that's
mean,
true.
none of my hair is gray in that picture.
Oh my God, that's right. That's back when you were blonde. Woohoo!
Yes, yeah, I was mostly bald still, but what was
Yeah.
left still had
Dude,
color.
you were bald at 21. I remember, I was there.
Yes.
But, so anyway, that's Thursday, May 4th, and then we've got a couple that are already out that we've recently published, Bringing Adaptive Leadership into IT, The Case for Agility, and Want to Improve Cybersecurity War Game. Those are both coming out. Also, please check out the attachment we've got, which is an issue paper on use cases for quantum computing. So we dig into all these fun things at some greater depth. Um, Last but not least, we are actually in the midst of our current research project, which is on AI. So if you would like to participate in some way, either you're a vendor, you want to tell us about your product, or you're a user and you want to tell us about your experience, go ahead and connect with us. Join the Nemertes community online at nemertes.com/community. Just mention that you're coming from Bright Talk and you want to participate in the AI study, and we'll take it from there. And last but not least, at the very end, this is who we are. You can read all that fun stuff. Oops. Um, so with that, the replay should be up on our channel shortly. If you found it valuable, please share it with your colleagues and take a moment to rate the webinar. Thanks very much. And that is it for this talk. Thank you for being here.
Thanks all.